Good day, everyone. We'll continue our study on the fundamentals of electrical engineering by investigating the generalized techniques for circuit analysis. The nodal and the mesh techniques are usually referred to as the generalized techniques, largely because they could be used to resolve any circuit type or structure. Unlike the voltage and current divider principles previously covered, which are designed for specific circuit structure. I mean, the voltage divider principle resolves series circuit type, and or better still, while the current divider rule applies to parallel circuit structure. But at this point, we'll be looking into these two techniques, how we could use them, or better still, use them in terms of analyzing any circuit structure. So let us begin with the nodal analysis. So, to be able to analyze any given circuit using the nodal technique, the node, or better still, the nodes in the circuit must be identified. And in our previous lecture, we established the fact that any point joining two branches or two or more branches in a circuit is a node. So this is a node. Okay, two or more branches. So should we have two or more elements joined together, the point at which they join is referred to as a node. And then we could extend this a little further. And then you see we have about 3 elements. And also in our previous lecture, we made mention of a type of node, which is the essential node. Okay, and this is the point joining 3 or more elements together. Now, one important point to note here is that the essential node in the circuit helps in identifying a proper choice for the reference node. Okay, so it's usually very, 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 very pertinent, let's put it that way, to be able to identify the essential node should we desire to use or decide to use or use or deploy the nodal technique, because the reference node is that point in the circuit we assign a reference voltage of 0 volts, more like grounding the circuit. Okay, grounding the circuit. Okay, so in this case, should we extend this some more? Let's say have something like this. You realize that this is an essential node. This is an essential node because we have 3 or more elements, and this is also an essential node. Okay, it's also an essential node. And some choices are better than some choices. And should we decide to pick any reference node? Well, as my own rule of thumb, you want to select a reference node that has some relationship or shares some relationship with the voltage sources. And in this case, this makes a proper choice. Okay, fine. So let us look at some of the basic steps required. So basic steps for nodal analysis. So the first point here is to identify the nodes. Identify the nodes. And also, afterwards, we designate a reference node. Okay? In the circuit. Now, we already established that the proper choice is to look out for the essential node, right? That is assigning a reference voltage of 0 volts, okay? Now, the next point is to specify the independent nodes, or nodes. Now, these are the nodes with unknown voltages. So usually you want to assign some variables, a V1 or V2 all the way. It could be E1, E2, depending on your choice. And the total number of unknown voltages gives us the total number of systems of equations we'll have to resolve in the circuit. So if we have 2 unknown voltages, then we're going to have 2 systems of equations. And 3 unknown voltages, 3 systems of equations. And then the third point here to note afterwards is to assign current directions to all the branches in the circuit. So assign current directions to all the branches in the circuit. Okay. And the convention we are going to be adopting is to show current leaving all the branches, all the nodes. Current leaving is currents leaving the nodes. So let's assume we have a circuit like this. Just draw a simple circuit. So let's assume we have a voltage source here. Let's assume we have a voltage source here. So this is 2 volts. Let's say this is 4 volts. Let's say this is 1 ohm, 2 ohms, and 3 ohms. So from what we have established so far, yes, we want to identify the nodes. This is a node, this is a node, this is also a node, and this is equally another nodes. These are points joining different elements or different branches, okay? And then you want to designate the reference node. And at this point, we said, well, an essential node, this is an essential node, this is also an essential node. But the one having some relationship or connection with the voltage sources may make a proper choice. And in our case, this just makes that perfect choice, okay? And we say Vref here is the same as 0 volts. And then We say to specify the independent nodes, that is identifying the nodes with unknown voltages. So now at this point, we have a voltage source here, and we know that voltage is usually applied across the terminals. So we have two terminals here, this terminal and this terminal. So the voltage of this voltage source with 2 volts value is going to appear across these two terminals, okay? And you see that this terminal is positive with respect to this terminal. So it's going to be positive 2 volts here. So meaning we know, we have an idea what the voltage value is at this node. And similarly, this terminal is negative with respect to this terminal and it has a value of 4 volts. So this is negative 4 volts. So the only node with unknown voltage here is this point, is this node. And we label it, say, V1. So that is our independent node. And we already established that the total number of independent node voltages or node voltage or known voltages determines the total number of equations that we'll be resolving. So in this case, we have one unknown voltage, and we are going to be having one equation, one system, a single system of equation. And then the next point is to assign current directions to all the branches. So here we show currents leaving the node. So this is a node, so current leaving this node, let's call it I1. That flows through the 1 ohm resistor. Then at this node again, we show current leaving this node. Let's say that's I2, and current also leaving this node, that is I3. Perfect. And we know these are passive elements, so current will definitely flow in through the positive terminal and exit through the negative terminal. Positive, negative. Perfect. So the next point here is to write KCL at the independent node. So the first thing to do here is to write KCL at the independent nodes. So here we have a single node. Then for us to write KCL at this independent node, so we want to write KCL at node 1. So it means that the sum of currents entering that node is the same as the sum of currents leaving that node. That is KCL at that node, okay? And so we have I1 going into this independent node, that is I1, is the same, I2 and I3 are flowing out, the same as the sum of the currents leaving the node, I2 plus I3. That's the fourth point. And as soon as we are done with that, then we try to express the currents in terms of the node voltages using Ohm's law. So the fifth point here is using Ohm's law, that's the fifth point rather, using Ohm's law, express the currents, that is this currents I1, I2, I3 in our case, in terms of the node voltages, in terms of, let's say they are node voltages, okay? So in order to do that, to do this by Ohm's law, we know that the current here is the voltage value divided by the value of the resistor. And at this point, this is positive with respect to this terminal, and V1 is negative with respect to this terminal. So I1 is the same as positive 2 volts. Let's change the color. That'll be positive 2 volts minus V1. That's 2 volts at this node, the voltage value at this node, minus the voltage value at this node, because it's negative. This terminal is negative with respect to this terminal, divided by 1 ohm. That is by Ohm's law. is the same as I2. Now, that's going to be the potential difference at this point, which is V1, which is positive, minus Vref, which is negative, with respect to V1. So that will be V1 minus Vref divided by 3 ohms plus I3, which is V1 minus, this node is negative with respect to this, but the voltage value is -4, then minus 4 divided by 2 ohms. Yeah, so we've established that point. So once that is done, we'll go on to the next point. We've gotten our equation. This is the system of equation. And then we'll go on to solve the system of equations, which are usually simultaneous equations. And then, because they are not quadratic, so the variables have the part 1, so they are simultaneous equations, and then we could use any of the known methods, the Cramer's rule and the matrix method, the substitution, elimination, whichever method we intend to use, depending on which we are comfortable with. And afterwards, we use the node voltages to evaluate the required electrical quantities. That's it. So let's consider one example. Let's assume we have a circuit. So this is positive, this is negative. Say this is 2 volts. This is positive, this is negative. Let's say this is 4 volts. This is 4 ohms. Here we have 10 ohms. Here we have 2 ohms. And here we have 5 ohms. That's it. Okay. So the first thing to do is to identify the node. So we have a node here. These are points where elements are connected together. It's also is a node. Okay. Then we also designate the reference node. And I said, well, as my own rule of thumb, just check out for the essential node that is connected to that is connected to a voltage source in the circuit. And this makes the perfect choice for us. This is also an essential node, this is an essential. So this makes a perfect choice for us. So do that, assign a voltage value, a reference voltage of 0 volts. So at this point, the circuit is connected to ground. Then we specify the independent nodes. So, and those are the nodes with unknown voltages. So we know the voltage at this terminal, which is +2 with respect to this polarity. That's +2 volts here. Why this is also positive, the polarity is positive, so that's +4 volts here. So we know the voltages at those terminals. So the nodes with unknown voltages are these two. So let's say we label them V1 and V2. And then we assign current directions, okay? And we show currents leaving the node. So from this node, if we show this current leaving this node, say I1, so we know these are passive elements, so current flowing through the positive terminal and exit through the negative terminal. We know for the sources, active elements, current flows in through the negative terminal. So you can see this is the direction of current flow, so you know that. So this is also positive, negative, positive, negative, positive, positive, positive. And at this node, current leaves this node. Let's call this I2. And current also leaves this node, let's say I3. Current leaves this node, let's say I4. And current leaves this node, let's say I5. So we are good. So afterwards, we write KCL at the independent nodes. So we have two independent nodes, V1, node 1, and node 2. So we are going to write two systems of equations. So in other words, we are going to be writing two systems of equations for the two node voltages. Okay, so the first point now is to write KCL at node 1. Okay, and that is the sum of currents into the node is the same as the sum of currents out of the node. That is KCL. So I1 flows in, then I2 and I3 flows out. I2 plus I3. And the next point is to write, or better say, express these currents with respect to the node voltages. Then we use Ohm's law. So by Ohm's law, I1 is V2, is 2 volts, which minus V1, because V1 is negative with respect to the 2 volts. So that will be 2 minus V1 divided by 1 ohm, by Ohm's law. And I2 is the current through the 4 ohm resistor, which is V1 minus Vref, which is V1 minus, because at this point, it is the reference voltage, which is 0. Vref divided by 4 plus I3 is the current through the 2 ohm resistor, which is V1, which is positive here, and minus V2, because this is negative here. So that will be V1 minus V2 divided by 2. Okay? Perfect. So if you multiply through by 4, for instance, to eliminate the denominators and perform all of the necessary operations, then we are going to get 8 is the same as 7V1 minus 2V2. So this is our first equation. Then we can now write KCL at node 2. Okay? So that's the sum of currents into the node is the same as the sum of currents out of that node. And the current into node 2 is I3, I3 flows in, while I4 and I5 flows out. I4 is I5. Then if we express these current values with respect to the node voltages, so I3 is V1 minus V2, V1 minus V2 divided by 2. That's by the 2 ohm resistor, while I4 is V2 minus Vref, V2 minus Vref divided by 10 ohm plus I5 now is V2 minus 4, V2 minus 4 volts divided by 5 ohms. Okay, so we know Vref You know, Vref is 0, so Vref is the same as 0 volts. So if we try to expand this, we know this is V1 minus V2 over 2, the same as V2 minus 0 divided by 10 plus V2 minus 4 divided by 5. So that's going to give us, if we multiply through by 10 to eliminate the denominator, say 10 into V1 minus V2 divided by 2, same as 10 to bracket V2, that's 0 minus 0, so 10 plus 10 to V2 minus 4 over 5. So that's going to give us 5 V1 minus 5 V2, which is the same thing as V2, plus 2 V2 minus 8. So take like terms and all of that, so we're going to get 8 is the same as minus 5 V1 plus 8 V2. So we have two systems of equations. So if we try to resolve the two systems of equations, which are 8 is the same as 7V1 minus 2V2, and then 8, which is minus 5V1 plus 8V2. Then should we use the matrix method? We know we have this 8, 8, the same thing as 7 minus 2 minus 5, 8, then V1, V2. So we can now resolve this using Cramer's rule, where the first is taking the determinant of this parameter, 7 minus 5 minus 2, 8, which is 7 times 8, which is 56, minus 2 times minus 5, that's positive 10, that's a minus 10. So this gives us 46. And then let's say delta V1. So we'll replace the first column with this parameter. So that will be 8 eighths minus 2 eighths. So then that will be 8 times 8. That's 64 minus 2 times 8. That's minus 16. So that's going to give us 80. Then delta V2. We now be replacing the second column by these parameters. That will be 7 minus 5, 8, 8. So that will be 7 times 8. That's 56 minus 5 times 8. That's minus 40. Minus 40. So that's going to give us 96. So V1 will be delta V1 over delta, which is 80 over 46, which gives us 1.74 volts, while V2 is the same as delta V2 over delta, which is 96 divided by 46, which is going to give us 2.09 volts. Well, you could use elimination method, substitution methods to resolve the two equations, but the point is we should get the same answers. It's that simple. So what's my point here? The most important point are these markers, okay? You must ensure you follow through on these markers. Now, once you screw up on all of these points, then everything may go wrong, okay? That's all for nodal analysis, okay? But we have a special case, which is that case, or better still, the circuit structure where we now have to use or deploy the supernode concept. Supernode concept. Okay. So, well, say that a supernode is a closed surface. Okay. And then KCL also applies to closed surfaces. So we say whenever you have two independent nodes directly connected by a dependent or an independent voltage source, then it becomes sufficient to apply the supernode concept. So let's just put it down. So whenever you have two independent nodes directly connected by a dependent or an independent voltage source, it becomes sufficient to apply the supernode concept to the node. Okay, so what are we talking about? So let's assume we have circuit like this. Let's say we have resistor here. Let's say then connected like this. Let's assume the current is flowing through here. So let's say this is 2 ampere. This is 4 volts. So let's assume we have a circuit like this. So let's say this is 2 ohms, 4 ohms, 8 ohms, 10 ohms. Now, we want to identify the nodes. These are the nodes here. These are the nodes, right? And this is also node. Straight off, we know this terminal is negative with respect to this terminal, so it's negative 4 volts. So we know a 2 amp current is flowing through this, okay? Now, we can tell the voltage at this point because 2 amp current flows through a 4 ohm resistor by Ohm's law, we can tell the voltage value. But here, we are unable to tell the voltage values, so these are the independent nodes we want to. And here we say whenever you have two independent nodes directly connected by a dependent source, now this is a dependent source, or an independent source. So when we designate independent sources, we use the diamond shape, okay, so plus minus, why this is the dependent, okay, so just to know, dependent and independent. Okay, and then we are able to now designate this as our reference node, VREF. But here we have two node voltages, and here we have, you know, an independent node voltage in between these parts. So this forms a supernode. So we have an independent voltage source in this case. What if it is a dependent voltage source? So let's wipe this for instance and say, well, this time we have a dependent voltage source in between. We have a dependent voltage source in between. So student. Let's assume this is 2Ix, and then Okay, let's make it simple. Let's assume this is Ix. So many is dependent on the current flowing in a particular branch. And let's assume that Ix is flowing in this branch. So it means the voltage, this dependent voltage source is dependent voltage source is dependent on some current value flowing in the branch. Good. The bottom line is whether it is a dependent voltage source or an independent voltage source, so long it is connected between two unknown voltages, meaning between independent nodes, then the supernode concept applies. Because at this point, we may not be able to identify the actual current flowing through, okay? So then we now treat this entire closed surface, as a supernode. And then we treat the currents flowing into this closed surface, flowing out, flowing out, flowing out. Okay? So in other words, we now treat this closed surface as a supernode. Okay? It's a massive node. Okay? So currents can flow in through and out of this node, then we can apply KCL and also KVL. So let's talk about the steps required in resolving such circuits. So, steps to resolving supernode problems. So the first is when the supernode concept applies, when the supernode concept applies, just like I said earlier, you apply KCL and KVL at the supernode. Just take note of this, okay? Previously, all we do is to write KCL at the independent nodes. But now that we have a supernode, we write KCL at that supernode because we have two nodes all put together this time. And then we also write KVL at that supernode. And then, second point is, once you have a dependent source, you must relate the dependent variables to the node voltages. Okay? So once and source, we must relate dependent variable to the node voltages. So in this case, we have IS, okay, as the dependent voltage source. So in other words, can we wipe all of those from it? So, okay. So in other words, once KCL and KVL has been written at the supernode, let's say for instance, this is I1, this is IX, then this is also IS. Let's call it, yeah. Let's say this is, let's just put up a proper convention. I2, I3, then I4. Let's say this is the I2, okay? No, it's IS. Okay. Now, KCL at this node will be KCL will be sum of currents into the node is the same as sum of currents out of this node. So we have I1 going in, I1 is the same as I2, I3, I4 coming out, I3 plus I2, I2 rather, I2, I3 plus I4. Okay, so can represent this in terms of the node voltages, which is still minus 4, is positive, negative. Okay, so let's assume there's a resistor here. Okay, it's not a short circuit. It's positive, negative, positive, negative, positive, negative. So this is V1, right? Minus V1, 2 is the same as I2 is V1 minus Vref, Vref divided by 8 plus I3 is V2 minus Vref, V2 minus Vref divided by 10 plus V2. Now, we have this current flowing in, so it's flowing in opposite direction, right? To our sign convention. So I4 will be the same as minus 2 ampere, right? So we don't have a voltage source here, so we can now present that there's I2 flowing here, but it's in opposite direction to our convention, so that's minus 2 ampere. Okay, so we've done that. So, okay, and then KVL at this point is to look at the voltage value. So here, V1 is positive with respect to V2, V2 is negative with respect to V2, to V2, so this is our first equation. So KVL at this point will be I2 is the same as V1 minus V2, right? Which is our second equation. Because this is negative, V2 is negative with respect to V1. Then you want to express, the last point is we want to relate the dependent variable in terms of the node voltages. That's I2. And I2 now is the voltage flowing through this branch, which is the same as V2, no, sorry, V1. Same as V1, sub 1, V1 minus Vref. Vref is 0 volts divided by 8. So I2 is the same as V1 minus 0 divided by 8. So I2 is the same as V1 over 8. This is our third equation. So that's how to go about the supernode concept. First, we write the KCL at the supernode. Then second, we write the KVL at the supernode. And once we have a dependent voltage source in between, then we'll have to express that dependent variable. In this case, I2 is the dependent variable in terms of their node voltages, which we just did here in our third equation. So let us look at one simple example. Okay, let us assume we have a circuit that looks something like this. We have a current flowing through this. So this time we have an independent voltage source. And Perfect. So here we have 1 ohm. We have 5 ohms here, and 9 ohms here. We have 5 ampere current here. We have 3 ampere current here. Then we have 9 volts here. Well, in resolving any circuit using the nodal analysis, we want to identify the nodes first. So that's the first thing to do. And you realize that some circuit structure may be confusing sometimes. But if you look at this point carefully, you will see that these 3 elements, the 1 ohm resistor, the 3 amp current, and the 5 ohm resistor are all connected on the same node. So in other words, this is a single node. We could rather modify this by putting them all at the same point, and then we'll have a slant on this point, okay? So they are all on the same node, okay? And then we have a 3 amp current flowing through, say V1. Then here again is another node, okay? Say V2. I think those are the 2 nodes. The point here is, okay, we also have the 3rd node, which is equally an essential node. Okay. Then should we take this as our reference node? Vref equal to 0 volts. Then you realize that we have 2 independent nodes connected by a single voltage source. So we can as well treat this as a super node. And treat this as a super node. Okay. Then we already know the current flowing into the node, and we know the current flowing out, say I1. We know this current is also flowing out, which is 5 ohm, and then this is flowing out, which is I2. So the first thing to do is to write KCL at this node. So write KCL at the super node, okay? Now that we have identified that it is a super node. Since the independent node voltages are connected by a voltage source, then it is a super node. So once we do that, the sum of currents into the node is the same as the sum of current out of that node. So we have 3 ampere flowing in. Okay, all other currents are flowing out. I1 is flowing out, I2 is flowing out, I5 is flowing out. Same as I1 plus I2 is 5. Okay, and once we move this, so that will be 3 minus 5 is the same as I1 plus I2, so that's minus 2. It's the same as I1 plus I2. And then by Ohm's law, by Ohm's law, so if we represent or express these current values by their node voltages, so that will be I1 is V1 minus Vref, which is 0 divided by 5, plus I2, which is V2 minus Vref divided by 9. So that's going to give us minus 2, same as V1 minus 0 divided by 5 plus V2 minus 0 divided by 9, because the reference voltage is 0. So that will give us minus 2 is the same as V1 divided by 5 plus V2 divided. Then this will give us, this now will give us minus 90 is the same as 9V1 plus 5v2. So that's our first equation. And in dealing with supernodes, we already established that once you write the KCL, you have to write KVL at that supernode. So KVL at the supernode will now give us at the supernode. So we have V1, V2 at this point. The voltage source is 9 volts, and V1 is positive with respect to V2, and V2 is negative with respect to V1. So that will be V1, so meaning this is V1 and this is V2 minus V2 is equal to 9. So this is our second. So in resolving the systems of equations, that is this and this, we get V1 to be the same as minus 3.214 volts, and V2 is the same as minus 12 plus 214 volts. That's simple, right? Okay. So let us look at mesh analysis. We already established in our previous lecture that a mesh is a loop that does not contain any other loop. So while a loop is any closed path in a circuit. So for mesh analysis to apply, the circuit has to be planned. So in other words, the circuit may be drawn on a plane surface such that no elements cross each other. Okay? So a few points to note here is that the exterior branches have their polarities fixed by the passive sign convention. Okay, I'm going to show all of this. The exterior branches have their polarities fixed by the passive sign. That's the first point. The second point is that mesh currents are strictly used for analysis because currents do not actually flow in the manner presented by mesh current directions, okay? So don't confuse mesh current direction with the actual current direction in the circuit. Okay, so let us consider the basic steps, okay? Basic steps for mesh analysis. So the first point here is to specify the currents flowing in meshes of the planar circuit. We specify the currents flowing in meshes of the planar circuit. Okay. The second point here is to write KVL around the meshes. So write KVL around the meshes. Then the third point is to use Ohm's law. Use Ohm's law to express voltages across the elements of the mesh current. And the next point is to solve a system of equations, which are usually simultaneous equations. And afterwards, you want to use the mesh currents, use the mesh currents to evaluate the required electrical quantities. Okay, simple, straightforward, really straightforward, okay? And let's look at one simple example. So let's assume we have a circuit. It looks something like this. So let's say this is 1 ohm, this is 2 ohms, this is 4 ohms, this is 5 ohms, this is positive, negative, 4 volts, it's positive, negative, 2 volts. So this is 3 ohms. Perfect. So the first thing we want to look into here is to specify currents flowing in the meshes, okay? Currents flowing in the meshes. So we have two meshes here, which is a loop not containing any other loop. Let's say this is IA, it could be I1, I2. This is another mesh. Let's say this is IB, okay? And afterwards, we want to write KVL around the nodes. But recall that we already said that the mesh currents in this case are strictly used for analysis. So they may not be in the same direction as the actual current flow in the circuit. So we must not confuse them, okay? And all the branches, we said all the exterior branches, all of these branches, all the exterior branches have their polarities fixed by the sign convention. So if that's the case, if current flows here, if current flows in this direction, for instance, then this is going to be positive. The external, we call not the internal branches, external branches. So this is positive. Current flows in through the positive terminal for passive elements, negative. Then this is the next external. So this is positive, this is negative. Same thing happens here. This is the external here, positive, negative. And this is positive, negative, okay? So the polarities are fixed according to passive sign convention. And then you see that these are the sources we have here. Current flows in through the negative terminal of the sources because they are active elements. And then we can tell the actual current direction in this case. I1 flows in this manner, okay? And let's say this is I1. Okay, so we can tell that I2 definitely flows in this manner, right? This is I2. But I3 doesn't flow this way now because looking at this mesh current flows from left to right, but the actual direction of current is determined by the 4 volts voltage source, and current flows from the negative to the positive, so current flows in this direction with respect to this voltage source, which is I3. So in other words, the actual direction of current, the actual current I3 current direction is the same as the negative of IB. So you must take note of this. while IA flows in the same direction as I1. So let us move on. So the next thing is to write KVL around the meshes. So KVL at mesh A, this mesh. So we have negative here, negative 2 ampere, current moves into the negative here. So negative 2 volts rather. Let's take that V off it. Then plus 1 times I1, IA rather, plus, now I2 flows flows into the 3 ohm resistor, and you see that I3 flows in the opposite direction. So if we say here 3 IA, since IB is in the opposite direction, so that will be minus IB. Okay. Right in this branch, because we have 2 currents flowing in this branch, IA and IB, following the mesh currents, following the mesh current direction rather. Then plus 4 times IA. It's the same as 0. And this is going to give us 8 IA minus 3 IB is the same as 2. It's our first equation. Then we write KVL at mesh 2 or B. Mesh B, that will be current flows into the positive terminal for voltage source. So that's positive 4 plus 5. It's 5 IB plus 3 IB, but this time IA flows in the opposite direction, minus IA plus 2 IB. It's the same as 0. This will give us minus 3 IA plus 10 IB B is the same as negative 4. So this is our second equation. So we have 2 systems of equation here. That is 8 IA minus 3 IB, the same as 2, and minus 3 IA plus 10 IB, the same as negative 4. And in solving these systems of equation, we get IA to be the same as 0.113 ampere, but IB is the same. Now, as negative 0.366 ampere. Now, this is what we get from this analysis. Now, for us to determine the current direction, I3 is the same as negative IB, which is going to be 0.366 ampere. While I1 is the same as IB, which is the same as 0.13 statement. Okay. So you can see that the mesh current IB does not give the actual direction of current, because I3, the actual direction of current is the same, is in the opposite direction as the mesh current. Okay, just like in the supernode, just like in the nodal analysis where we had a special case where a voltage source is connected between 2 unknown voltages, or better still, between 2 independent nodes, which led to the supernode concept. The same thing applies in the mesh analysis, where we have the super mesh concept, where a current source is connected between two meshes. So let's assume in this case, we have this branch replaced by a current source. So let us write this, for instance. Okay, no worries. Let's just write this and then talk a bit about the super mesh concept before solving an exam. Okay, so let's say super mesh concept. So a super mesh is equally a closed path in a circuit that does not include the current source. Okay, so take note. A super mesh is a closed path in a circuit that does not include the current source. So a super mesh exists when you have a current source between two meshes, like I said earlier. A super mesh exists when you have a current source between two meshes. So the major steps here, let's just say the step required in resolving super mesh problem is that when the super mesh applies, then you apply KVL and KCL at the supernode. Then all other things remain. Okay, so let us look at one quick example. So let's say we want to replicate this circuit. So positive, negative, positive volts. It's a current source, and then current source, so 2 ampere. So negative, positive here. So this is 4 volts. So we have 4 ohms here, 3 ohms here, 2 ohms here. Okay. Good. So far, we've been able to identify the direction of this current. It's downward. Now, we have two meshes, I1, I2, okay? But the bottom line is we have a current source here, not a passive element. And the external elements have their polarities assigned by the passive sign convention. So this is positive, negative, this is positive, negative, right? So this is positive, negative, and this is positive, negative. Okay. So this leads to a supernode problem. And here we say a super mesh problem, sorry, it's a super mesh problem, not a super mesh problem. So in other words, the super mesh is that closed path that does not include the current source. So this is the super mesh. So when you trace around the meshes without necessarily including the current source between the meshes, then we have a super mesh. So what do we do? Write KVL. Write KVL. So write KVL around the super mesh. And here, current goes into the negative terminal. That's -2 plus 1 times I1. That's current in this loop. 1 times I1. Then we come to this next loop plus 2. Current flowing in this loop is I2. It's I2. Then minus 4. Then plus 3. I2 plus 4 is I1 here. I2 0. And then this gives us 5I1 plus 5I2 is the same as 6. Yes, that gives us our first equation. Then we also write KCL at the 2 ampere source. Okay, this 2 ampere source. Now, we know that the actual current direction in this case is that current flows into the negative terminal of the voltage source. So meaning it's going upward this way, so this flows this way. So let's say this is I1. How about I2? It flows in through the negative terminal. So this is also moving out this way. It goes through the negative terminal, so that's the actual current direction. Let's call this I2. Okay. So it means that at this point, I1 flows into this node while the 2 ampere current and I2 flows out. So by KCL, sum of current into the node is the same as sum of current out of the node. And that gives us I1 flows into the node. I1 is the same as 2 ampere flows out and I2. 2 plus I2. Okay? So from this, we get I1 minus I2 is equal to 2. It's our second equation. So once we resolve these two systems of equations, then we get I1 to be 1.6 ampere and I2 to be the same as negative 0.4 ampere. Note that I1 is in the same, the I1 mesh current is the same direction, while I2 mesh current is the same direction with I2. So we have something good here. I think that's about it. So at some point, you want to wonder, how do we really decide which method to adopt? Because whichever way, a circuit we could resolve using a nodal technique could be resolved using a mesh technique. And a circuit we can as well resolve using a mesh technique could be resolved using a node technique. Okay? So how do we determine the best method? Okay? How do we determine the best of the two generalized techniques given a circuit? How do we do that? So you want to look into the method that results in few unknown. Okay? So we say, well, the first thing to do is to adopt a method that results in fewer unknowns, okay? And then also use the circuit structure to decide, okay? Use the circuit structure to decide. So you know, if we have a super mesh, for instance, then the mesh technique serves the purpose. And if we have a super node in the circuit, then the nodal technique does the job. Okay? And also, you may want to decide using the required electrical quantities. Okay? Required electrical quantities. So if we have to solve for voltage, then I think the nodal technique serves the purpose. And if we have to solve for current, then the mesh analysis may be sufficient. Well, I think we'll end the class here and hope to see you some other time. Bye for now.